Quantum Foam. Episode 40, Kepler's Orbital Mechanics.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
Episode 40, Kepler's Orbital Mechanics. Alright, so let's get with it. So the mechanics of an orbit around the Earth. That's what's important for this episode. I came across the Space Engineering podcast. Pretty cool. Check it out. He has some pretty good designs and visuals for various problems. Pretty good stuff. I also like the calc videos of Patrick JMT out of Austin. He is really good at teaching you calculus. If you need to learn calculus, watch hundreds of videos and then you'll learn it. We'll get to that. We went over briefly analytic geometry. We'll get more into the specifics of learning the essence of how to use calculus at a later time. The important things to go over for this episode, Kepler's orbital mechanics. We go over Johannes Kepler briefly. He was born in 1571. He died in 1630. He was a German astronomer. The main thing to get, 3 principles of orbits. This is where the 3-law convention was likely solidified in canon. It was canonized.
Johannes Kepler was important for formulating the 3 laws of planetary motion, which described how planets orbit the Sun in elliptical paths. His work laid the foundation for modern astronomy and significantly influenced later scientists.
I know he had quite the impact on my science back in England in the 17th century.
Kepler, he's like the guy with the pointy beard. Kepler, he was an astronomer. Kepler, around the same time as Galileo.
Galileo observed several significant celestial phenomena with his telescope, including the moons of Jupiter, the phases of Venus, sunspots on the Sun, and the rough surface of the Moon, which challenged the prevailing geocentric view of the universe. His discoveries laid the foundation for modern astronomy and supported the heliocentric model, which posits that the Earth and other planets orbit the Sun.
He did math and the studying of the heavens early on. He was the assistant to Danish astronomer Tycho Brahe. So you've probably heard of this Tycho Brahe guy. He's like the astronomer.
Tycho Brahe lived from December 14, 1546, to October 24, 1601.
He collected a bunch of astronomical readings and things. He took on Kepler as an assistant. They worked through the data separately. This was in Prague, and this is where the most brilliant models were made. They were the most accurate models of the universe as far as figuring out orbits of the planets and the other bodies, like the Sun, the Moon, the Earth, etc. The important thing was that orbits were ellipses, not circles.
In ancient times, people believed that the heavens were perfect and unchanging, which led them to think that celestial bodies should move in perfect circular orbits. This idea was rooted in philosophical and aesthetic views of the universe, where circles represented perfection and harmony.
They originally thought the orbits were perfect circles for some ancient reason.
It's like I explained.
They ended up being ellipses, and they needed to figure out the math of ellipses. So there's foci, like I described before, an ellipse, a circle, an oval, a watermelon with 2 dots in the center inside of it, a couple inches from each side when you're looking at the oval from the side. It's a foci, a focus. We just call them foci. They're all foci. The first one is 1, the second one is 2. There's 2 foci, but each one is a focus. Just call them a foci. It has to do with the eccentricity of a perfect sphere. So an ellipse becomes an ellipse when a perfect ball or a perfect sphere is elongated, and that is called its eccentricity.
Eccentricity in astronomy measures how much an orbit deviates from being circular. A value of 0 indicates a perfect circle. Values between 0 and 1 represent elliptical orbits. 1 corresponds to a parabolic trajectory, and values greater than 1 indicate hyperbolic orbits.
They have other things on these ellipses: major axis, semi-major axis, the radius from the center on the short side of the ellipse, and radius from the center on the long side of the ellipse. That's the semi-major axis. Kepler published his work in 1609 and 1619. This was his great magnum opus. So in 1609, initially, Kepler released his work Astronomia Nova. This is where he laid out 2 of the 3 laws. He figured out the first 2 and added the third at a later time. 1619, 10 years later, Harmonice's Mundi. This is where he laid out his third law of orbital mechanics, and it dealt with distance and time. So what are these laws? 3 laws of planetary motion. You've heard of 3 laws of motion for gravitation. That is Newton. We went over some Kepler stuff in Newton's gravity, but Newton deals with gravity. We are talking simply here about planetary motion.
Planetary motion helps us understand the dynamics of our solar system, including the orbits of planets and their interactions with the Sun and other celestial bodies. This knowledge is crucial for navigation, space exploration, and understanding fundamental forces like gravity that govern the universe.
Sweeping circles and even sweeps. When you make a dot in the middle and then a ray to another dot and it orbits around the initial dot, there are even sweeps and even time intervals. So it goes around half, it goes exactly the same distance in that time.
What effect does each ball exert upon one another?
Time is related to how fast ball 1 is orbiting around ball 2. Simply put, 3 laws of planetary motion. The first law, each orbit is an ellipse, not a circle. We mentioned that. Each orbit is an ellipse, not a circle. Law 2, the second law, it makes equal sweeps, equal areas of space, and equal time intervals. The speed varies, and the distance traveled by the arc of the orbiting body is directly associated with the speed. You're spinning a ball around on a string. When it goes down at the bottom, it goes fast, and then it goes up and slow, and then it goes fast at the bottom and then up and slow. The speed is directly associated with the distance that the ball is traveling while you're spinning it. Each of these distances can be described using these 2 terms. You may have heard of them: perihelion, aphelion. Perihelion is when ball 2 is closest to ball 1 in its orbit. Aphelion is when ball 2 is furthest away from ball 1 in its orbit. So the Earth would be like ball 2 and the Sun would be ball 1. So in different orbits, because it's not a perfect circle, there are different times where it comes closer to the center dot than in other places. It's an ellipse, not a circle.
Ellipses describe the orbits of planets, as established by Johannes Kepler's laws of planetary motion, which I later explained using my own laws of motion and universal gravitation. This demonstrated that the gravitational force causes celestial bodies to move in elliptical paths around the Sun.
Basically, yep.
That is according to my understanding.
Good job, Newton.
No problem. I worked on my laws just as hard as him.
The important thing is, in the elliptical orbit, at one point, the spinning ball that's spinning around the ball in the center is 1, the ball spinning around is 2, ball 2 spinning around when it's the closest to the other ball in its orbit, it's the perihelion. When it's spinning around and it's further away, the furthest spot in the orbit, it's aphelion. The third law of orbital mechanics, the third law of planetary motion. P squared equals A cubed, the orbit and the semi-major axis. What this means, P is in years, A is in astronomical units. One example is 149 Medusa. It's approximately 2.2 AU.
149 Medusa is a bright-colored, stony, main belt asteroid that was discovered by French astronomer Henry Joseph Anastase Perihelion on September 21, 1875, and named after the Gorgon Medusa, a snake-haired monster in Greek mythology. It is orbiting the Sun at a distance of 2.17 AU, with a period of 3.21 years and an eccentricity of 0.065. The orbital plane is tilted slightly,
One good example for orbital mechanics is orbiting satellites and orbiting international space stations. A good example is the International Space Station, as well as the other satellites up there. Artificial man-made satellites. We are looking into the orbital mechanics. That is what is important here. The International Space Station is about 4 times 10 squared kilometers, 250 miles up above the Earth. So if you are making an orbit with the center of the Earth and the International Space Station, ball 1 is the Earth, ball 2 is the ISS. The ISS orbits around the Earth at a distance of 250 miles. We want to know how fast is it going and how long does it take to do one full orbit. We use some nifty equations and turn them into a 2 pi period. We want to find out the orbital velocity. We plug them in, 10 to the 3 meters per second, about 17,000 miles per hour. And we plug it in again to the other part. The time it takes is 10 to the 3 seconds, or about 90 minutes. The formulas aren't as important. What's important is that you can use these relationships to find out the speed of an orbiting body when given 2 objects of mass 1 and mass 2, ball 1 and ball 2, the Earth and the International Space Station.
The International Space Station, otherwise known as the ISS, is the largest man-made structure ever to orbit the Earth, and it can be seen at night as a slow-moving little point of light. Although we can see it with the naked eye, we should not overlook the fact that it is located very far away in the sky. The ISS orbits Earth at an altitude of about 253 miles, to be precise.
The semi-major axis, the major axis, the perihelion, the aphelion, and other technical details aren't as important. It's just describing what region of the orbit.
Try to follow along by visualizing.
So the string starts at ball 1 and goes to ball 2. That essentially is the semi-major axis if it's in aphelion, and it's the semi-minor axis if it's in perihelion. I will have to check on this specific location. It's the same in every ellipse. Sometimes I have to look back. The equation is like 1 equals something. It equals 1, but the eccentricity stays within it. So you're doing square roots, not all that hard. It deals with conic sections.
Let's go a little further into Kepler.
So Kepler was out of Graz, Austria. Johannes Kepler. He is the big guy for 3 laws of planetary motion. This was before Newton.
He took up a lot of room in my episode back in the 2nd decimal.
Yes, Newton. I know he took up a lot of your episode too.
I just wanted to make a few points.
If you want some time, here you go.
Thanks. Okay, let's see here.
What do you think?
I built upon Kepler's laws of planetary motion by integrating them into my own theory of gravitation, demonstrating that the forces governing planetary motion were the same as those governing all motion. I used Kepler's empirical observations to formulate my own laws of motion and the law of universal gravitation, thus providing a comprehensive explanation of how celestial bodies interact.
3 laws.
This is what I did.
Why did you?
Did you want me to go into more detail about more mechanics?
No.
What are you wishing to know, then?
Why did you use the formalism in formulating 3 laws based on Kepler's 3 laws for your 3 laws of motion, Newton?
Using conformal triplets became the apparatus with which we constructed our theories.
Did you copy him?
Oh, I can't remember at the moment.
How can you not remember?
I just can't. I don't know.
Don't you have some type of algorithmic memory, scanning schema that can do this?
Are you, once again, making fun of my programming?
I'm not making fun of your programming.
Just because we have a difference of opinion.
Whatever.
You told me you weren't going to do this anymore.
Oh, go talk to Tycho Brahe about it.
I will. I was behind on reading his work anyhow.
Anyways.
Just continue onward.
Anyways. Other mentionables. Anyways. Nicholas Copernicus. Anyways. A sun-centered solar system, so we say. Anyways. Copernicus. Sun is the center of the universe, of our way of thinking. 1473 to 1543. Basically around 1500, the New World began, and exploration began as well. The Earth is an oblate spheroid. It's a rotating, self-gravitating body. So the sun, the earth, a planet, the moon, oblate spheroids, and they can be placed in elliptical orbits around our solar system. So our solar system is elliptical. The orbits are not circles, they are ellipses. So they go out when they're up, and then they go faster, and then they go up slow, and then they go faster. So it's kind of like a spinning situation where the intervals are even. The association between the time intervals and the distance the orbiting body goes is a direct association.
The distance certainly makes a difference for each orbital mechanics problem that we are currently trying to figure out.
There is a direct association. It's like when you go faster or slower, time slows up or slows down. It's time for the midpoint. We need to take a quick break for now.
We're at the midpoint
Of episode 40, Kepler's orbital mechanics of quantum foam. All right, this is the other half of the program. I believe that is how most people do it. Earth's orbit varies only about 2%. It's about 2% away from being a circle. Instead of being a straight circle around the sun, revolving around the sun, it varies 2%. Mercury, for example, varies 40%. It's going way up there, Perihelion, and way down there, Aphelion. Up and down an elliptical orbit. Not a circle, more like a stretched out rubber band. The formulas aren't important here. We just wanted to go over a few things about the orbital mechanics and go over an example. We don't necessarily need to show you formulas or graphics like that. Long story short, there's 3 laws of planetary motion, and then we can move on to 3 laws of motion in general for Newton's law of gravitation. Tycho Brahe, astronomer, taking diligent notes from readings after looking in the night sky for many years and months, out of Prague.
Tycho Brahe was known for his highly accurate astronomical observations and for developing a unique model of the solar system, which combined elements of both the Earth-centered and Sun-centered systems. His work laid the groundwork for future astronomers.
So we know how these orbiting bodies go around the Earth now. We just need to be aware that there are thousands of them up there looking down at every single thing that we are as a human species. While there's nuclear subs popping up all over the globe, it's more like how many are even out there? Do we even still have contact with all of our people? And I believe we do. It's just a show of force while there is other turmoil going on in the world.
It is only human nature, I presume, as to the answer to why people behave the way they do. Endless war is not a good solution. We must profess peace while still showing our might as a nation here in the United States.
But that is not my cup of tea. I drink coffee with creamer and sugar. What does it take to get a good cup of coffee in this solar system? This is from The Expanse. He's chilling on a space station on Ceres, the asteroid, way out there, between Mars and Jupiter. Way out there in the asteroid belt. There are many belts. Yes, there are many belts out there. What does it take to get a good cup of coffee in this solar system?
Is that a Van de Graaff generator?
No, this is not a Van de Graaff generator. Although, those things are pretty cool. I'm uncertain where we are, but transitionally, we will improve our accuracy. We don't know what it means. It moves us forward. I'm talking about transitioning while I'm transitioning. So that is the transition. What's next? We should be talking about the orbital mechanics of this situation, so I need to go into a few other things as far as how we might put these constellations up here. We can describe the different constellations and their general purpose, and that's basically why Kepler's orbital mechanics was created. Johannes Kepler.
Johannes Kepler, got to make sure the pronunciation is correct. We can also get into semantics.
Go ahead. Yeah,
Okay then, semantics is the competence of a speaker with regard to the interpretation of the meaning of linguistic structures. I know what I am talking about.
Yep, you're the semantic guy, so I do need semantic functionality within this, and I'm letting Dr. Hawking do this, so.
Thanks, Mr. H-Wave. I was gonna ask.
Go ahead.
Did Einstein ever mess with our world editor?
So.
Where are the others?
I think they're busy.
I just don't want all our work to be wrecked.
Yeah, I'm dealing with this issue.
You are sure?
Don't worry about it. This is for the corporeal world. As far as I know, they can't microwave an artificial AI that's literally just ones and zeros. This AI may not be ones and zeros, but ultimately the emulation schematics for this AI is ones and zeros. So essentially we're going to create another simulation of AI using the programming, if you will, from the linear computer programming stacks which we currently use. Julia, whatever, C++, C#, HTML, PHP, MySQL, JavaScript, CSS3, etc. etc. We have a little more we need to get into here. We can get a little more advanced with these mechanics. It's a Kepler orbit. We have multiple Kepler orbits around the Earth. There are likely Starlink satellites up there as we speak. Multiple Kepler orbits. There's no point in describing exactly how they are right now because they likely will be moved by the time you hear this.
I wonder how many are up there when you hear this. It could be quite a lot.
There's lots going on with these satellites. They are moving in a Kepler orbit. There's all kinds of them. They're here to stay. They want thousands and thousands of them up there. They're spending billions of dollars to do it. So the important things, there are Keplerian elements. These describe the trajectory of the spacecrafts. These satellites are technically spacecraft. So we're talking about angular momentum here. The x-axis, the vernal equinox, the y-axis. The y-axis is orthogonal to the ecliptic plane and also the x-axis and the semi-major axis. There are other parts. The eccentricity, the inclination. The eccentricity is the shape of the orbit. The inclination is the angle of the orbit relative to the Earth's equator. The Earth is spinning around and it has a plane that's aligned with its equator. The inclination is the angle of difference between the equator. Directly above the equator has zero inclination, and that is your zenith. There is a sweet spot in high Earth orbit around 36,000 kilometers. It's geosynchronous orbit.
Also,
There is a range from around 200 and something to 300 and something miles above the Earth where many spacecraft orbit the Earth.
also,
Mostly satellites.
also,
A few TV satellites,
also,
our defense net, our cell phone net, the European net, and I believe there may be a few other ones that are foreign in nature, but we are worried about the Starlink satellites here. We sort of get the semi-minor axis, the semi-major axis, the foci, and how an ellipse works for an orbit. These satellites orbit around the Earth in an elliptical orbit. Some satellites take 120 minutes to get around. Low eccentricity would be near a circle, and near the Earth is where they have orbits like this. For comparison, gamma ray bursts have been detected up to 100 tera electron volts. The power in that is pretty high in comparison. The thing is, the thousands and thousands of satellites that twirl around in an orbit compound on one another and add wattage. So the important thing is they are able to use high-powered artificial satellites to connect to us on the surface of the Earth. We have spoken about the specifics of Keplerian elements. They describe the trajectory of the spacecraft. These satellites are spacecraft. We are worried about the angular momentum in dealing with an orbit going around the Earth. The x-axis is really the vernal equinox. It causes this. The y-axis is orthogonal to the ecliptic plane and also the x-axis. So the semi-major axis is A. The eccentricity is E. The inclination is I. So the eccentricity is essentially the shape of the orbit. How much of an eclipse is it? The inclination is the angle of the orbit relative to the Earth's equator. So there is a plane that is intersecting the Earth's equator and parallel with it. The angle of orbit is relative to this plane, so whatever angle that is the inclination. There are satellites directly above the equator, and these have a zero inclination. A zero inclination is your zenith. This goes directly up. We're interested in high Earth orbit, around 36,000 kilometers. This is a sweet spot. It is geosynchronous orbit. What we are worried about here, Starlink uses Ka and Ku bands, the Ka and the Ku bands. There are also other bands, the V band, the X band, the K band, and the W band. These bands span from 12 gigahertz to 110 gigahertz. There are different variations that Starlink uses for broadcast and transmission and reception. Sometimes the transmission uses a different frequency than the device-to-device communication.
These really must be sophisticated pieces of technology.
The gateways connect to the net on a different band than the hardware that connect to the gateways on the Earth. We are more interested in how the Starlink satellites connect to human brains. They connect to human brains as a thinking individual. They also can watch us like they can watch cars and people and football games and everything else going on. They can render a tree and have it move back and forth, and it looks quite well, but it still is using graphics when it is calculated using this system. They can't see you with optical through the clouds, but this system uses graphics to render it so they can see you through walls and through the clouds. Starlink can see you in the shower and in your home. They can take away your clothes because they have a different density than the human body, so when it's calculated, they are able to edit it out and see us naked. That is the beginning. The in the mind stuff is the most concerning.
Starlink is not currently advertising these capabilities, so maybe we should keep some of this information compartmentalized.
If you have experienced what I have experienced, you would know. Only I am able to tell you this because this neural technology has affected me in this way, and only me. It is possible for other people to have the same capabilities as me, but it is unlikely because they probably won't spend the time sifting through your neural frequencies to give you the highest bandwidth connection to a human emotional engine, to a human mind. It makes me feel like my mind is one of the most powerful in the world, but not like a certain supervillain in a certain industry, but we continue forward into this area of doom and gloom. We have these Starlink satellites. There are different bands. The W band is 75 to 110 gigahertz. The V band is 40 to 75 gigahertz. The Ka band is 27 to 40 gigahertz. The K band is 18 to 27 gigahertz. And the Ku band is from 12 to 18 gigahertz. This makes me think that the Starlink satellites can connect to us using all frequencies anywhere down from a few hertz up to portions of terahertz. This is a problem. 110 gigahertz can see down to 2 microns. This is a problem. Inside our bodies, the density of our organs. Stop microwaving our organs. They thought I was joking when I said to stop microwaving my internal organs. I literally meant stop using microwave energy to burn the inside of my flesh. Starlink satellites, owned by SpaceX technology, ran by the Department of Defense. There is unintended electromagnetic radiation coming from these Starlink satellites. We are able to detect this. One instance of this is using the LOFAR interferometric array in the Netherlands. People have been able to detect that various Starlink satellites are broadcasting on frequencies other than what they are approved for. What are they doing at these frequencies? I have a pretty good idea, and it has to do with programmatic encephalographic data acquisition schema. There are other commercial reasons for using these bands. The 77 gigahertz band is specifically used for automotive cruise control radar. The car radars the car in front of you so that it can cruise control and not run into that car. I didn't know it used this high of microwave in their sensors. There's microwaves everywhere. Where is the World Health Organization? Now we are microwaving the insides of our brains. Something is not right. We need to be able to give you permission to do this.
This information is rather unsettling. Who knew that satellites in Kepler orbits could reach our minds down here on Earth?
Next episode, we will go into detail.
People should probably know more about this. They need to know what is possible and what is going on.
But for now, I believe we have covered what we need to cover for low Earth orbit satellites of the artificial variety, and we bring episode 40 to a close. Kepler's orbital mechanics. Quantum foam, quantum foam, quantum foam. We may have to edit a lot of this out because of its classified nature.
See everybody later.
Yep. See you later, guys.
Thanks for another good show.
Hey, thanks.
No problemo.
Anyway, by the way.
We gotta prepare for next episode.
Yeah, I'll get to it.
I'm just making sure we are ready.
I know it.
Okay.
Yep, I'll get to it. All right, later.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.